Now, we are going to solve a sample problem in simple harmonic motion and uniform circular motion. How do we link simple harmonic motion to uniform circular motion? So the problem goes this way. Suppose a 0.5 kilogram glider attached to the end of an ideal spring, so it means it obeys Hooke's law, the spring obeys Hooke's law, with force constant or spring constant, which is equal to 450 Newton per meter, undergoes simple harmonic motion in frictionless horizontal plane with an amplitude of 0.4 meters. So we're going to compute the following. First is the angular frequency. Next is the frequency, the period, the maximum speed of the glider, the maximum magnitude of acceleration of the glider, the speed of the glider 2 seconds after it is released from the uh, maximum displacement, or what we call the amplitude, and then the acceleration at the same time is 2 seconds, as well as the displacement at the same time. Okay, so let's solve first the angular frequency. Before that, you need to set your scientific calculator into radian mode. Scientific calculator into radian mode. Let us solve first for letter A, the angular frequency. Now, if this is the spring, attached to it is a mass M, and then it is oscillating in a frictionless horizontal plane. So there are two forces acting on the glider. One is of course, the force acted on it to stretch the spring, that's F of A. And the other one is F of R, the force exerted by the spring. These two forces are equal, but acting in opposite direction. So F of R equals F of A. So F of R is negative Kx, and F of A is MA. Now, what is the position as a function of time of an oscillating object? The position x is expressed in terms of amplitude cosine of omega t, which is equal to the mass of the object attached to the spring, and then the acceleration of an oscillating object as a function of time is amplitude times omega squared cosine of omega t. Alright. And then we can cancel the amplitude, cosine omega t, and then the negative sign. So you have K equals mass times omega squared, or omega squared equals the spring constant over the mass attached to the spring, or omega equals the square root of the spring constant K over the mass attached to the spring. So we can solve for the angular frequency given the spring constant and the mass attached to the spring. So let us solve for letter A. So A as the angular frequency equals the square root of the spring constant over M, the mass attached to the spring. So again, make sure your calculator is in radian mode. The square root of the spring constant, 450 Newton per meter, over the mass attached to the spring, which is 0.5 kilogram. Then 450 divided by 0.5 square root. Then we have the angular frequency equals 30 rods per second. So it can move 30 rod in 1 second. It can rotate. So for an object rotating, it can rotate 30 rods every second. Okay. Now, how about the frequency? That's letter B. Frequency B, since omega is expressed, which is equal to 2 pi f, then the frequency is angular frequency over 2 pi. We have the angular frequency, which is 30 rad per second. So this is 30 rad per second over 2 pi. Then frequency here, f, equals, calculator, 30 divided by 2 times 3, 40. Approximately 4.77 hertz. So it can move from the positive amplitude to negative amplitude, then back to positive amplitude in 1 second. The next, letter C. Letter C, the period. Since frequency is reciprocal to the period, 1 over t, then period is 1 over f. So period here equals, what's the frequency? 1 over 4.77 hertz. So that's 1 divided by 4.77. The period equals 0.21 seconds. So that's the period. So it takes 0.21 seconds to move from the positive amplitude, then go to negative amplitude, then back to positive amplitude. So that's the period. Next, the maximum displacement and the maximum speed of the glider, 30. So V equals the amplitude times omega. That's the maximum amplitude. Speed, the amplitude is 0.4 meters times the angular frequency, which is 30 rad per second. Then the maximum speed should be 12 meters per second. We have the speed. Next, the maximum acceleration, it's letter E. Maximum acceleration, A, is the amplitude times the square of the angular frequency. Then that's 0.4 meters times the square of the angular frequency. The angular frequency is 30 rad per second. Squared. Then the maximum acceleration is 360 meters per second squared. Okay. We have the acceleration, maximum acceleration. Next, the speed. The speed of the glider at t equals 2 seconds, or the speed of the glider 2 seconds after it is released from the initial position. The initial position is the amplitude. Then we have the speed as a function of time. It's letter F. We have speed as the function of time is the amplitude, omega, sine of a negative amplitude, omega, sine omega t. And that is equal to negative 0.4 times 30 rad per second sine of 30 rad per second times 2 seconds. Let us compute. So how the speed is negative 3.67 meters per second. So that's the speed. Next, the acceleration of the glider at time 2 seconds. It's letter G. G. So what's the acceleration? 2 seconds after the glider is released. The acceleration as function of time is amplitude times negative amplitude times omega squared cosine of omega t. Right. Then the amplitude is 0.4, so you have negative 0.4 meters times 30 rad per second quantity squared. Then cosine of 30 rad per second times 2 seconds. We'll compute. We have acceleration at time equals 2 seconds, 342.87 meters per second. So that's the acceleration 2 seconds after it is released. Okay, next, the displacement or the position of the oscillating system 2 seconds after its release from the initial position. It's letter H. So the position as function of time is cosine the amplitude, cosine of omega t. So the amplitude is 0.4 meters, cosine of omega, the angular frequency, which is 30 rad per second, times 2 seconds. Right? Let's compute. Cosine of then we have the position is negative 0.38 meters. Okay. When the amplitude is positive, these two quantities, the position and the acceleration of oscillating system, must be in opposite direction. So if the acceleration is positive, then the position is negative. If the position is positive, then the acceleration is negative. In this problem, acceleration is positive, then expected that the position of the oscillating system is negative. So you have negative 0.38 as the position, and the acceleration is 342.87. That's positive.